we silence notifications? I promise I'll go live at 10. I didn't promise I'll be ready at 10. But I'm basically ready, y'all. Here we go. I'm JD, Nicholas Jensen Denton. This is my pharmacopoeia. Thanks be to the ancestors. Thanks be to the giants. Thanks be to the wisdom. I am here to finish Einstein's autobiographical notes. We left off, and now we're picking up back on page 69. And we're going to move forward with the notes. With the notes. Welcome back. Let me just make sure I'm live real quick before we jump into it. Going over to JD's Pharmacopoeia. View channel. Stay with me. We're live. And let me just do a sound check. Sound check is good. I always think I'm too quiet. Testing. Testing. All right, I'll try to stay loud. Thank you for joining me. I'm going to silence the bowls, quiet bowls. Here we go. So starting at the top of the page. To do the latter, however, is obligatory if one wants to do justice to the equality of gravitational and inert mass by means of the basis of the theory, and if one wants to overcome Mach's paradox as concerns the initial systems, then one must give up the attempt to give the coordinates an immediate metric meaning, parentheses, difference of coordinates equals measurable lengths or times, end parentheses. One will not be able to avoid treating as equivalent all coordinate systems which can be created by the continuous transformations of the coordinates. The general theory of relativity, accordingly, proceeds from the following principle. Natural laws are to be expressed by equations which are covariant under the group of continuous coordinate transformations. This group replaces the group of the Lorentz transformations of the special theory of relativity, which forms a subgroup of the former. This demand by itself is, of course, not sufficient to serve as a point of departure for the derivation of the basic concepts of physics. In the first instance, one may move his incense into a safer position. There we go, back. Give me a second. This demand by itself is, of course, not sufficient to serve as point of departure for the derivation of the basic concepts of physics. In the first instance, one may even contest the idea that the demand by itself contains a real restriction for the physical laws, for it will always be possible thus to reformulate a law, postulated at first only for certain coordinate systems, such that the new formulation becomes formally universally covariant. Beyond that, it is clear from the beginning that an infinitely large number of field laws can be formulated which have this property of covariance. The eminent heuristic significance of the general principles of relativity lies in the fact that it leads us to the search for those systems of equations which are in their general covariant formulation the simplest ones possible. Among these, we shall have to look for the field equations of physical space, fields which can be transformed into each other by such transformations describe the same real situation. The major question for anyone doing research in this field is this: of which mathematical type are the variables, functions of the coordinates, which permit the expression of the physical properties of space, structure, question mark. I did not realize that was a question. Let me go back. The major question for anyone doing research in this field is this: of which mathematical type are the variables which permit the expression of the physical properties of space? Only after that, which equations are satisfied by those variables? The answer to these questions is today by no means certain. The path chosen by the first formulation of the general theory of relativity can be characterized as follows. Even though we do not know by what type, field, variables, or structure physical space is to be characterized, we do know with certainty a special case, that the, quote, field-free space in the special theory of relativity. Such a space is characterized by the fact that for a properly chosen coordinate system, the expression ds squared equals dx1 squared plus dx3 squared plus dx3 squared minus dx4 squared. You can go read that on page 71 if you want. Belonging. All right, so such a space is characterized by the fact that for a properly chosen coordinate system, the expression aforementioned belonging to two neighboring points represents a measurable quantity, square of distance, and thus has a real physical meaning. Referred to an arbitrary system, this quantity is expressed as follows: ds squared equals ga dx subscript 1 dx subscript 2, whereby the indices run from 1 to 4. The g the g with a generic indice form a real symmetrical tensor. If, after carrying out a transformation on field 1, the first derivatives of the g with respect to the coordinates do not vanish, there exists a gravitational field with reference to this system of coordinates in the sense of the above consideration. A gravitational field, moreover, of a very special type. Thanks to Riemann's investigation, probably got his name wrong, sorry. Riemann? Riemann sounds nice, actually. Thanks to Riemann's investigation of n-dimensional metric spaces, this special field can be invariantly characterized. Riemann's curvature tensor R IKLM subscript formed from the coefficients of the metric 2 vanishes. 2. The orbit of a mass point in reference to the inertial system relative to which 1 is valid is a straight line, therefore an extremal geodetic. The latter, however, is already a characterization of the law of motion based on 2. The universal law of physical space must now be a generalization of the law just characterized. I now assume that there are two steps of generalization: A, pure gravitational field, or B, general field, in which quantities corresponding somehow to the electromagnetic field occur too. The instance A was characterized by the fact that the field can still be represented by a Riemann metric 2, i.e. by a symmetric, I've been reading too much of the Bible. 2, i.e. by a symmetric tensor, whereby, however, there is no representation in the form 1 except in infinitesimal regions. This means that in the case A, the Riemann tensor does not vanish. It is clear, however, that in this case a field law must be valid, which is a generalization or loosening of this law. If this law also is to be of the second order of differentiation and linear in the second derivations, then only the equation to be obtained by a single contraction, 0 equals r subscript ki equals g superscript I am r subscript IKLM. I'm not a physicist. You must understand. I am kind of retarded, so I'm not going to be able to explicate these physics meanings, as you know. Anyways, to be obtained by a single contraction came under consideration as field equation in the case of A. It appears natural, moreover, to assume that also in the case of A, the geodetic line is still to be taken as representing the law of motion of the material point. It seemed helpless to me at that time to venture the attempt of representing the total field B and to ascertain field laws for it. I preferred, therefore, to set up a preliminary formal frame for the representation of the entire physical reality. This was necessary in order to be able to investigate, at least preliminarily, the usefulness of the basic idea of general relativity. This was done as follows. In Newton's theory, one can write the field law of gravitation thus: delta phi equals 0. Oh, God. Oh, my Greek teacher's going to be pissed. Is that a phi? That's not a phi. Is that a psi? Hold on. Chat, I'm cooked. Oh! It is not a... yes, it is a psi. I was correct the first time. So, in Newton's theory, one can write the field law of gravitation thus: delta of psi equals 0. Psi equals gravitation potential at points where the density of matter, rho, vanishes. In general, one may write Poisson equation delta psi equals 4 pi k rho, which is 4 p kappa rho. For my Greek heads, rho equals mass density. In the case of the relativistic theory of the gravitational field, r takes the place of delta psi. On the right side, we shall then have to place a tensor also in place of rho. I don't like that script of the psi. Oh, fuck. It's a phi. It's a phi. Ah. Guys, it's a phi. Most of y'all know it as phi. But if you say phi, I'll say faux fum. It is a phi. And I fail at Greek. My life is a sham. It's all over. Fuck, man. We're good. I'm gonna stop beating myself up. Delta phi equals 0. Delta phi equals 4 pi kappa rho. Rho equals mass density. In the case of the relativistic theory of the gravitational field, rho takes the place, or r, I don't know, now they're confusing me with all the conflating languages and physics. Big R takes the place of delta phi. Phi, fo, fum. On the right side, we shall then have to place a tensor also in place of rho. Since we know from the special theory of relativity that the inert mass equals energy, we shall have to put on the right side of the tensor of energy density more precisely the entire energy density, insofar as it does not belong to the pure gravitational field. In this way, one gets the field equations R equals 1/2 G of any subscript multiplied by R, which might be a capital Rho, I'm not sure, which equals a negative kappa multiplied by tau, which has to stand for time. I'm not sure again. Man, read the equations if you want. The second member on the left side is added because of formal reasons. For the left side is written in such a way that its divergence disappears identically in the sense of the absolute differential calculus. I never read Principia Calculatio. The right side is a formal condensation of all things whose comprehension in the sense of a field theory is still Damn it! Fire. Oh, my myrrh! Oh, it's okay. Fire. Simmer down. Fire. It's a lie. All right. That was scary. Oh, shit. If anybody listens to this podcast or this audiobook, I love you, man. I need to break that myrrh up for sure. Oh, we're going back. We're not going to miss a beat. I missed a beat. The second member on the left side is added because of formal reasons. For the left side is written in such a way that its divergence disappears identically in the sense of the absolute differential calculus. The right side is a formal condensation of all things whose comprehension in the sense of a field theory is still problematic. Not for a moment, of course, did I doubt that this formulation was merely a makeshift in order to give the general principle of relativity a preliminary closed expression, for it was essentially not anything more than a theory of the gravitational field, which was somewhat artificially isolated from a total field of as yet unknown structure. If anything in the theory as sketched, apart from the demand of the invariance of the equations under the group of the continuous coordinate transformations, can possibly make the claim to final significance, then it is the theory of the limiting case of the pure gravitational field and its relation to the metric structure of space. For this reason, in what immediately follows, we shall speak only of the equations of the pure gravitational field. The peculiarity of these equation lines on the one hand, in their complicated construction, especially their nonlinear character as regards the field variables and their derivatives, and on the other hand, in the almost compelling necessity with which the transformation group determines this complicated field law. If one had stopped with the special theory of relativity, i.e. with the invariance under the Lorentz group, then the field law, R subscript something equals 0, would remain invariant also within the frame of this narrower group. But from the point of view of the narrower group, there would at first exist no reason for representing gravitation by so complicated a structure as is represented by the symmetric tensor G subscript something. If, nonetheless, one would find sufficient reasons for it, there would then arise an immense number of field laws out of quantities, all of which are covariant under Lorentz transformations, not, however, under the general group. However, even if of all the conceivable Lorentz invariance laws, one had accidentally guessed precisely the law which belongs to the wider group, one would still not yet be on the plane of insight achieved by the general principle of relativity. For, from the standpoint of the Lorentz group, two solutions would incorrectly have to be viewed as physically different from each other. if they can be transformed into each other by a nonlinear transformation of coordinates, i.e., if they are, from the point of view of the wider field, only different representations of the same field, one more general remark concerning field structure and the group. It is clear that in general one will judge a theory to be the more nearly perfect the simpler a structure it postulates, and the broader the group is concerning which the field equations are invariant. One sees now that these two demands get in each other's way. For example, according to the special theory of relativity, the Lorentz group, one can set up a covariant law for simplest structure imaginable, a scalar field, whereas in the general theory of relativity, a wider group of the continuous transformation of coordinates, there is an invariant field law only for the more complicated structure of the symmetric tensor. His homemade Macedonian liquor is fucking strong. We have already given physical reasons for the fact that in physics, invariance under the wider group has to be demanded, with a annotation that this is the physical reason to remain with the narrower group, and at the same time to base the relativity theory of gravitation upon the more complicated tensor structure implies a naive inconsequence. Sin remains sin, even if it is committed by otherwise ever so respectable men. It's getting dogmatic on us. We have already given physical reasons. Yep, just read it. Sin is a sin, brother. 42 to 42. I can see. No, okay. He's talking about sacrifice. Yeah. A wider group has to be demanded. From a purely mathematical standpoint, I can see no necessity for sacrificing the simpler structure to the generality of the group. The group of the general relativity is the first one which demands that the simplest invariant law be no longer linear or homogeneous in the field variables and in their differential quotients. This is of fundamental importance for the following reason. If the field law is linear and homogeneous, then the sum of two solutions is again a solution. As for example, in Maxwell's field equations for the vacuum, in such a theory it is impossible to deduce from the field equations alone an interaction between bodies, which can be described separately by means of solutions of the system. For this reason, all theories up to now required, in addition to the field equations, special equations for the motion of material bodies under the influence of the fields. In the relativistic theory of gravitation, it is true the law of motion, geodetic line, was originally postulated independently in addition to the field law equations. Afterward, however, it became apparent that the law of motion need not and must not be assumed independently, but that it is already implicitly contained within the law of the gravitational field. The essence of this genuinely complicated situation can be visualized as follows. A single material point at rest will be represented by a gravitational field which is everywhere finite and regular, except at the position where the material point is located. There, the field has a singularity. If, however, one computes by means of the integration of the field equations the field which belongs to two material points at rest, then this field has, in addition to the singularities at the positions of the material points, a line consisting of singular points which connects the 2 points. However, it is possible to stipulate a motion of the material points in such a way that the gravitational field which is determined by them does not become singular anywhere at all except at the material points. These are precisely these motions which are described in first approximation of Newton's laws. One may say, therefore, the masses move in such fashion that the solution of the field equation is nowhere singular except in the mass points. This attribute of the gravitational equations is intimately connected with their nonlinearity, and this is a consequence of the wider group of transformations. Now, it would, of course, be possible to object. If singularities are permitted at the positions of the material points, what justification is there for forbidding the occurrence of singularities in the rest of space? This objection would be justified if the equations of gravitation were to be considered as equations of the total field. Since this is not the case, however, one will have to say that the field of a material particle may the less be viewed as a pure gravitational field the closer one comes to the position of the particle. If one had the field equation of the total field, one would be compelled to demand that the particles themselves would everywhere be describable as singularity-free solutions of the completed field equations. Only then would the general theory of relativity be a complete theory. Before I enter upon the question of the completion of the general theory of relativity, I must take a stand with reference to the most successful physical theory of our period, the statistical quantum theory, which, about 25 years ago, took a consistent logical form. Shout out Schrödinger, Heisenberg, Dirac, Born. This is the only theory at present which permits a unitary grasp of experiences concerning the quantum character of micromechanical events. This theory, on the one hand, and the theory of relativity on the other, are both considered correct in a certain sense, although their combination has resisted all efforts up to now. This is probably the reason why among contemporary theoretical physicists there exists entirely differing opinions concerning the question as to how the theoretical foundation of the physics of the future will appear. Will it be a field theory? Will it be, in essence, a statistical theory? J.D. postulates, will it be a theory of virtual reality and information as a fundamental construct of reality? Does reality equal information? Only physics experiments will tell. If you don't know what I'm talking about, Google virtual reality experiments, Caltech, Tom Campbell. You'll discover them. Physics is an attempt conceptually to grasp reality as it is thought independently of its being observed. Facts. In this sense, one speaks of, quote, physical reality. In pre-quantum physics, there was no doubt as to how this was to be understood. In Newton's theory, reality was determined by a material point in space and time. In Maxwell's theory, by the field in space and time. In quantum mechanics, it is not so easily seen. If one asks, there's my psi, I knew it was coming. If one asks, does a psi function of the quantum theory represent a real factual situation in the same sense in which this is the case of a material system of points or of an electromagnetic field? One hesitates to reply with a simple yes or no. Why? What the psi function at a definite time asserts is this: what is the probability for finding a definite physical magnitude, Q or P, in a definitely given interval, if I measure it at time t? The probability is here to be viewed as an empirically determinable and therefore certainly as a, quote, real quantity, which I may determine if I create the same psi function very often and perform a Q measurement each time. But what about the single measured value of Q? Did the respective individual system have this Q value even before the measurement? To this, there is no definite answer. Within the framework of the existing theory, that is, since the measurement is a process which implies a finite disturbance of the system from the outside, it would therefore be thinkable that the system obtains a definite numerical value for Q, or P, i.e., the measured numerical value, only through the measurement itself. For the further discussion, I shall assume two physicists, A and B, who represent a different conception with reference to the real situation as described by the psi function. I knew psi was going to be important. A. This is A physicist. The individual system, before the measurement, has a definite value of Q, i.e., P. Why? Why we got to be two things? For all variables of the system, and more specifically, that value, which is determined by a measurement of this variable. Proceeding from this conception, he will state the psi function is no exhaustive description of the real situation of the system, but an incomplete description. It expresses only what we know on the basis of former measurements concerning the system. The individual system, before the measurement, has no definite value of Q, i.e., P. The value of the measurement only arises in cooperation with the unique probability which is given to it in view of the psi function, only through the act of measurement itself. Proceeding from this conception, he will, or at least he may, state the psi function is an exhaustive description of the real situation of the system. We now present to these two physicists the following instance. There is to be a system which at the time t of our observation consists of two partial systems, S1 and S2. Oh my God, are we getting chemical? Which at this time, no we're not, are spatially separated, and in the sense of the classical physics, are without significant reciprocity. The total system is to be completely described through a known psi function, psi 2, in the sense of quantum mechanics. All quantum theoreticians now agree upon the following. If I make a complete measurement of S1, I get from the results of the measurements and from psi 2 an entirely definite psi function, psi 2 of the system, S2. The character of psi 2 then depends upon what kind of measurement I undertake on S1. Now, it appears to me that one may speak of the real factual situation of the partial system S2. Of this real factual situation, we know to begin with, before the measurement of S1, even less than we know of a system described by the psi function. But on one supposition, we should, in my opinion, Einstein's that is, absolutely hold fast. The real factual situation of the system S2 is independent of what is done with the system S1, which is spatially separated from the former. According to the type of measurement which I make of S1, I get, however, a very different psi 2 for the second partial system. Psi 2, psi 2 to the first. Now, however, the real situation of S2 must be independent of what happens to S1. For the same real situation of S2, it is possible, therefore, to find, according to one's choice, different types of psi function. One can escape from this conclusion only by either assuming that the measurement of S1 telepathically changes the real situation of S2, or by denying independent real situations as such to things which are spatially separated from each other. Both alternatives to me appear entirely unacceptable. If now the physicists A and B accept this consideration as valid, then B will have to give up his position that the perceived function constitute a complete description of a real factual situation. For in this case, it would be impossible that two different types of perceived functions could be coordinated with the identical factual situation of S2. This statistical character of the present theory would then have to be a necessary consequence of the incompleteness of the description of the systems in quantum mechanics, and there would no longer exist any ground for the supposition that a future basis of physics must be based upon statistics. It is my opinion that the contemporary quantum theory, by means of certain definitely laid down basic concepts, which on the whole have been taken over from classical mechanics, constitutes an optimum formulation of the connections. I believe, however, that this theory offers no useful point of departure for future development. This is the point at which my expectation departs most widely from that of contemporary physicists. They are convinced that it is impossible to account for the essential aspects of quantum phenomena, apparently discontinuous and temporally not determined changes of the situation of a system, and at the same time corpuscular and undulatory qualities of the elementary bodies of particles, by means of a theory which describes the real state of things, objects, by continuous functions of space for which differential equations are valid. They are also of the opinion that in this way one cannot understand the atomic structure of matter and of radiation. They rather expect that systems of differential equations which would come under consideration for such a theory in any case would have no solutions which would be regular or free from singularity everywhere in a four-dimensional space. Above everything else, however, they believe that the apparently discontinuous character of elementary events can be described only by means of an essentially statistical theory in which the discontinuous changes of the systems are taken into account by way of the continuous changes of the probabilities of the possible states. All of these remarks seem to me to be quite impressive. However, the question which is really determinative appears to me to be as follows. What can be attempted with some hope of success in view of the present situation of physical theory? At this point, it seems it is the experiences of the theory of gravitation which determine my expectations. These equations give, from my point of view, more warrant for the expectation to assert something precise than all other equations of physics. One may, for example, call on Maxwell's equations of empty space by way of comparison. These are formulations which coincide with the experiences of infinitely weak electromagnetic fields. This empirical origin already determines their linear form. It has, however, already been emphasized above that the true laws cannot be linear. Such linear laws fulfill the superposition principle for their solutions, but contain no assertions concerning the interaction of elementary bodies. The true laws cannot be linear, nor can they be derived from such. I have learned something else from the theory of gravitation. No ever so inclusive collection of empirical facts can ever lead to the setting up of such complicated equations. A theory can be tested by experience, but there is no way from experience to the setting up of a theory. Equations of such complexity as are the equations of the gravitational field can be found only through the discovery of a logically simple mathematical condition which determines the equations completely, or at least almost completely. Once one has those sufficiently strong formal conditions, one requires only little knowledge of facts for the setting up of a theory. In the case of the equations of gravitation, it is the four-dimensionality and the symmetric tensor as expression for the structure of space, which, together with the invariants concerning the continuous transformation group, determine the equations almost completely. Our problem is that of finding the field equations for the total field. The desired structure must be a generalization of the symmetric tensor. This group must not be any narrower than that of the continuous transformations of coordinates. If one introduces a richer structure, then the group will no longer determine the equations as strongly as in the case of the symmetrical tensor as structure. Therefore, it would be most beautiful if one were to succeed in expanding the group once more, analogous to the step which led from special relativity to general relativity. More specifically, I have attempted to draw upon the group of the complex transformations of the coordinates. All such endeavors were unsuccessful. I also gave up an open or concealed raising of the number of dimensions of space, an endeavor which was originally undertaken by Kaluza, in which, with its projective variant, even today has its adherents. We shall limit ourselves to the four-dimensional space and to the group of the continuous real transformation of coordinates. Change my light up a little bit. That's not... Oh, shiza. Give me 2 seconds. I just need my light is... Oh, the yellow. Oh, the yellow. There it is. I want that one. Okay. Carry on. We shall limit ourselves to the four-dimensional space and to the group of the continuous real transformation of coordinates. After many years of fruitless searching, I consider the solution sketched in what follows as the logically most satisfactory. A little translation error there from somewhere. I feel like, oh shit, fuck. Oh, we're good. My electronics are getting wet. Oh, fuck. Sorry, folks. Sorry for my language. Oh, shit. One moment. Oh, we're getting there. Don't try to live stream and drink Macedonian liquor at the same time. It's not worth it. I mean, liquor itself's not even worth it. Oh, it's so harsh. My coworker made it. It's so harsh. Oh, it's a little bit extra methanol in there. They kept the tails and the heads. Extra tails, extra heads, please. Oh, God. We're golden. All right, carry on. In place of the symmetrical G equals GKI, the non-symmetrical tensor G is introduced. This magnitude is constituted by a symmetric part SIK and by a real or purely imaginary antisymmetric AIK. Thus, G of IK equals S of IK plus A of IK. Viewed from the standpoint of the group, the combination of S and A is arbitrary because the tensors S and A individually have tensor character. It turns out, however, that these GIK, viewed as a whole, play a quite analogous role in the construction of the new theory as the symmetric G of IK in the theory of the pure gravitational field. This generalization of the space structure seems natural, also from the standpoint of our physical knowledge, because we know that the electromagnetic field has to do with an antisymmetric tensor. For the theory of gravitation, it is furthermore essential that from the symmetric G of IK, it is impossible to form the scalar density square root of GIK, as well as the contravariant tensor G to the power of IK, according to the definition, G of IK, G to the power of some integer equals delta of K to the power of 1, otherwise known as the Kronecker tensor. If you know, you know. I don't know. These concepts can be defined in precisely corresponding manner for the non-symmetric G of IK, also for the tensor densities. In the theory of gravitation, it is further essential that for a given symmetrical field, G of IK field, a field F prime of IK can be defined, which is symmetric in the lower indices and which, considered geometrically, governs the parallel displacement of a vector. And analogously, for the non-symmetric G of IK and non-symmetric T prime of IK can be defined according to the formula G of IK 1 minus G of IK, no fucking clue. What was that? Capital gamma? No. It's like some letter I've never seen before. Oh, wait. Just kidding. It is a capital gamma. G of IK minus G of IK gamma prime subscript V minus GIS gamma prime equals 0, comma, dot, dot, dot. Figure it out yourself. Equation A, page 93, which coincides with the respective relation of the symmetrical G, only that it is, of course, necessary to pay attention here to the position of the lower indices in the G and gamma. Just as in the theory of asymmetrical G of IK, it is impossible to form a curvature R prime KLM out of the gamma and a contracted curvature R KI. Finally, with the use of a variation principle together with A, it is possible to find compatible field equations. And he lists 4 field equations. I'm not going to do it. Each of the 2 equations, B1 and B2, is a consequence of the other. If A is satisfied, RKI means the symmetric, RKI the antisymmetric part of RKI. If the antisymmetric part of G vanishes, these formulas reduce to A and C1. The case of the pure gravitational field. Sounds nice. I believe that these equations constitute the most natural generalization of the equations of gravitation. Maybe I should study these. The proof of their physical usefulness is a tremendously difficult task, inasmuch as mere approximations will not suffice. The question is, what are the everywhere regular solutions of these equations? This exposition has fulfilled its purpose if it shows the reader how the efforts of a life hang together and why they have led to the expectations of a definite form. Institute for Advanced Study, Princeton, New Jersey, signed Albert Einstein. Let me read the last sentence. This exposition has fulfilled its purpose if it shows the reader how the efforts of a life hang together and why they have led to expectations of a definite form. I don't know. I like the beginning there quite a bit when he was being all philosophical, and then in the middle there he got all very science, physics, equations, like mind-numbing linguistic freaking tornadoes that is clearly for an elite class of alien minds of society who concern themselves with these types of scribblings on the paper. I don't get it. I never studied physics. I didn't even get to calculus, man. And I didn't want to do it. I didn't want to do it, man. I didn't even want to do chemistry, but I did it, and I struggled through it. And I just kind of did this to try to just let the information permeate a little bit. And I get the philosophical aspect of the whole thing, and he's trying to prove, it seems, that there is a definite form in reality, a true physical external thing which we can objectively measure, but it seems we have a bunch of incoherent different theories about the nature of reality, and the whole thing ends on the question that he doesn't answer. What are the everywhere regular solutions of these equations? It's it's open to physics. Nobody knows. Where are the solutions to the regular solutions of these equations? And I have not been led to the expectation of a definite form through this exposition. But I feel like there is a definite form. I feel like there is a definite form, and that is God. And can we measure that outside of ourselves? If we could, it wouldn't be this fucking hard, would it? It wouldn't be this damn confusing. It wouldn't be only for the elite alien minds, the super intellectual among us, who create new lexicons and vernacular systems and linguistic ruses. It's not ruse, but I guess there's logic and reason to it, but it eludes me. It's a conflation of multiple different languages and measurements and theories that I just have to use. The common man, the layman, has to trust that they build onto each other and they produce something in the end. You gotta ask, what is this stuff producing? Who, where, and when are these four equations which are fundamental to the theory of gravitation? So-called natural equations. I'm sure they use them somewhere. I don't doubt it. But, is it really explaining what we want it to explain, what Einstein wants it to explain? How the efforts of a life hang together? I don't know, man. It's hard. It's hard. If you stuck through this, man, if you listened through me running back and forth and getting my Greek wrong and the fire alarm, you're a goat, man. You are the greatest of all time if you listen to this. And, if you're a physicist out there and you understood anything as to what was going on, tell me this exposition fulfill its purpose. And that's all I got, folks. Thanks for staying with me.